All righty. I'm sorry I'm starting a little late. The other class went, excuse me, I got 10. No, that's not 10. Do I really have 10 chats? I shouldn't have taken that bathroom break. Hold on. Do I really have 10 chats already? That's good that you guys are on. I have some, I don't think so. Does someone have the invite to send him? Good. Thank you for doing that, you guys. Okay. And I just finished teaching this really exciting course, the algorithms course. We're in a neat place in there. So I'm a little, my mind is thinking algorithms, not so much what we're supposed to be doing here. So where did we end up? Where did we stop last time?
I believe it was the birthday paradox.
Very good. That's what I think. That was what I was thinking about. So thank you for confirming that. But you know what? Before we get started, there's a couple of people that haven't arrived. I mean, more than a couple. It's 10 people. Let me throw out something for the exam. Do you guys? You guys have all looked over the problems, right? You've seen the problems.
Yeah.
There's a problem in there about. Forgive me. Stop me if I'm incorrect. But 4 numbers, right? Distinct numbers, and you randomly make 3 comparisons, right? You understand comparisons between 2. You would find out which one's less and which one's bigger. Okay. Just make sure we're all in the same. I just want to make sure we're all in the same ballpark with that problem. What number was it?
8. It's question 8.
Yeah. Can I just get you? I just want to. Sometimes I do this at the beginning of the class just to encourage people to come on time. But anyhow, so we have 4 numbers, right? So A, B, C, and they're distinct. So we're going to take 3 comparisons, right? And based on those comparisons, we ask ourselves, do we know the sorted order now? And do we know the sorted order? And if you have a Hasse diagram, I don't know if you've seen these diagrams, but this diagram means that we know that A is bigger than B, is bigger than C, is bigger than D. So the sorted order from least to greatest is going to be what? D, C, B, A. So if we had made comparisons that supported this, we had enough information to ascertain that, then we would have, we'd have the sorted order of the numbers. But that's not always the case, right? Could you tell me 3 comparisons that between them that just would not give you enough information to determine the sorted order? Can you give me some comparisons? Comparison between 2 of them, Give me some. I might need to have some glory here. Somebody says I don't think so. No, 4 new messages. Okay.
So you want us to make 3 comparisons that wouldn't give us enough information?
Yes, I just want to make sure everybody understands. Yeah.
So like A to B, A to C, and A to D?
Excellent. That's exactly what I was thinking. Is to be on the same frequency, because I was thinking of that. So A to B, suppose the result was A less than B, A less than C, and A less than D. Very good. By the way, I like that example. So what would be the Hasse diagram? This is a partially ordered set that's trying to it's visually expressing the information that you get out of these comparisons. So what would it look like?
So A is less than. So
Right.
you'd have A on the bottom,
Right.
and then 3 lines above it going to B, C, and D, but they don't connect, or you can't tell which one's higher or lower than the other.
Exactly. Very good. Thank you very much. It's clear to me that you already looked at the tests, and I really have to say that this is great that people will look, because when I was a student, I didn't look at the tests until the last night. And, of course, the problem with that is you don't retain any insights that you get. But this is right. So when a person sees this kind of problem, they say, what do we do? There's no formula or something. Well, this is typical of my exams, is that I give small enough problems so that you can enumerate all the possibilities, okay? So let's think about this. How many comparisons are possible? I'm assuming we don't repeat a comparison, okay? So, you know what I mean? We're talking about 3 different comparisons. How many comparisons could be made if you have 4 numbers, A, B, and C, and D? How many could you make? This is a review of our counting principles.
You want me to keep answering or somebody else speak up?
Let's get.
Yeah.
I think you know the answer, but I just want to. Let me try to help other people. Let me try to help. You've got 4 numbers, right? When you make a comparison, that's a binary operation, right? You're going to compare A to B, for instance, as binary. You're taking 2 of them, right? So how many ways can I choose 2 of these numbers from 4? How many ways can you choose 2 from 4? This is. Are you good? Are you good with this? Well, everybody, you know what happened? Everybody just froze their video because they don't want to be. I promise you, I will never pick on anybody in this class. I would never do that. In fact, if you have your video on, I really respect that because it helps me to know how bad my jokes. No, I mean, sorry. It's what the terrible thing is. If I try to come up with a new joke, and I say, I'm driving into work, I say, oh, that sounds funny, and then somebody's got this frozen, face like this. Well, we're all young, right? You don't get this kind of effect. You get this in West LA. No, but anyhow, you get that frozen smile. And I say, God, did that go over well? And then I'm looking at that face, and so that face is saying, that was terrible, but I'm going to smile. It's hard to talk to a frozen face. It really is. I mean, if you guys can help me, I'm not a bad guy. I'm kind of a nice guy. So if you can help me out by letting me see your face. And just if I'm going to get fired for a bad joke, a reball joke, I want to know that you got it. It's like some kind of compensation for some stupid joke. Okay, so let's get back. We have 4 things. How many ways can you choose 2 things from 4 things? That's critical, you guys. When you leave the course, you should know this by heart. If somebody stopped you on the street and said, what's 4, choose 2? You should, can't even, forget it. It's Parkinson's. No, what is it? What's 4, choose 2? This is a binomial coefficient. The number of ways to choose 2 things from 4 things. You should know this. What is it?
6.
Good. Thank you. You got that a frozen smile too. What happened? No, I'm kidding. 6. So what are the combinatorics for this problem? There's only 6 possible ways of comparing these. So what happens in this problem? You're going to do what? There's only 6. You might as well list them all, and then you're going to have to choose. There's only 6 comparisons possible, and what happens? So let's write them out. I know this is a little bit driving people crazy, maybe, but here are your 6 comparisons. And what did the problem say? You're going to choose randomly, right? 3 of them. So let me do that. Let's do this real. This is no PowerPoint going on here, okay? Just pick 3. Is that going to do it? How many ways can I pick 3 from 6? So here's one selection. So I got to know how many ways can I pick 3 from 6. Well, it's not an incredible amount. 6 choose 3 is what? What is it? 15? 6? Uh-oh. It looks like it's 20. Is that right?
Yes.
So there's only you don't have to use any fancy mathematics here. You could just simply list them all out. You can look at all 20 ways. You can receive the information to find out how many of those lead to the sorted order. I mean, you just calculate. You don't need any. You don't need to be fancy here. Did that make any sense to anybody? These are the only these are the only ones possible, and you're randomly choosing 3, right? So you could break this down. You can figure out it's equally likely sample space. Just figure out how many lead to this sorted order. Did that help, or you want more? Did that help at all, or should I give more clarification? We're up to 28 people. Any more clarification? I'm surprised nobody has any kind of problem.
I do have a question.
Okay, good, Brandon.
So you only chose 3, but why?
Oh, isn't that what the problem says? Maybe I got it wrong.
Oh, I haven't seen that
You should,
specific problem. I haven't looked.
yeah, you choose. Stop me if I'm wrong, but you choose 3 comparisons at random, and then what is the probability that from those 3 you can figure out the sorted order?
Okay.
I don't think you're going to do it with these 3 right here. What happens if you take those 3 that I showed? What happens? Okay, suppose you have A less than C less than D. I guess it depends. This problem might be a little harder because it might depend on the result of the. Because just because you choose these, you still have the question of the result. So it could be a little harder. It could be a little harder, but let me just suppose this was the result. What do we get out of this? So you have A, and it's less than C, and it's less than A is less than C and D, but what do we know about C and D? So C is less than D. Okay? But there's no B. You haven't compared, we don't have any information on B, so we can't possibly get the sorted order. So at least for this, if this was the result, it wouldn't be helpful. Okay, I'll leave it at that. So the problem is, it's not trivial. I get it. But I believe it can be done by exhaustion. You don't need a fancy, anything fancy. Okay, I think it's time to get back to the, at least I hope this got you at least started thinking about it. Okay. Yeah, I guess you have to keep track of which one's larger than others, because sometimes you get in a situation where you already know the result of a comparison from the previous information. Okay, so there's something to worry about. It's a good problem, is what I'm saying. It's not obvious. Okay. Any other question on the test I should get to? I mean, like understanding the problem, the statement.
I have a quick question about it's not the final one because there's 2 extra credit problems, but number 9. So it says consider a cubic 4x4x4 tic-tac-toe playing cube.
Yes.
And it's an adjacency problem, but I'm just curious because it makes the problem much, much harder. Are you counting diagonals also as adjacent?
No, those would be, no.
Okay,
to be
good.
adjacent, they have to be flush.
Okay, perfect.
So the diagonal would be like, if you had one of your cubes was here, and the other one was here, right? Right? They do share a point, but they're not, I don't call that adjacent. Adjacent has to be flush.
Okay, good.
But glad you brought that up. Does anybody?
Much harder.
Oh yeah, no. But does anybody? Is there anybody that doesn't know cubic? They haven't played it. I think I asked that last time. What is the board for cubic? It's 3D, right? 3D tic-tac-toe. What does it look like? What does it look like? There's a cube, a big cube that's made up of smaller cubes. But the question is, how many smaller cubes? Okay. Well, it's 4 by 4 by 4. The big one. You have 4 on each 4 by 4. So how many is that total? What's 4 cubed? CS guys.
64.
64, right. So how do we get a hold of this problem? Does it have, for instance, does it have a center cube? A cube that's right in the middle of everything? When I say cube, I'm talking about these little cells in here. It's made out of 64 little cells. Does it have a center? Is there one that's like unique?
Oh, I mean, this is something that I was asking because I haven't played this before. Is this something where we're only using the surface squares, or we're using all of the cubes?
The little cubes.
So all 64.
Yes.
Okay.
And it turns out in the middle, you've got like eight of them that are sort of in the middle, but there's no one that's exactly in the middle. You have to go 5 by 5 by 5 for that. But it's hard to visualize this a little bit. So, so what people do sometimes is they draw the levels like an architectural diagram. So that would be like this. Okay, so this would be the first level. So to try to explain this guy right here would correspond to this part of the cube, that face on the bottom. Okay, and this one here would correspond to the top. So this horizontal 4 by 4 that's on the top. So sometimes this helps to analyze problems like this. So if you're taking two cells at random, suppose you choose this. First of all, I'll stop there. Is everybody okay with this? You've seen architectural diagrams, right? Where they go one, floor 1, floor 2, floor 3, floor 4. Okay, so this is the first one, second one, third. They do something. It's like you've done.
I've seen that in level editors.
Yeah, so you have it's levels. The idea is levels, right? Mm-hmm. Sometimes people look at this and they say, that doesn't look like a cube to me. Well, these are the floors. Floor 1, 2, 3, and 4. 1, 2, 3, and 4. So just to give you an idea. So, I mean, what if your first cube was here? The first that you took, you're choosing 2, right, at random? So if that's your first, you chose that cell, that little cublet inside. How many cubelets are adjacent to that? And where are they? Where are they?
You have, if that's the bottom layer, you have one directly above it, and then the 4 on each side.
Okay, is that all the ones that are adjacent to that? Adjacent means they share a face, they're flush.
There should be one on the second level, the one directly above it, right?
Good. It sounds like you've played Cubic before.
I had my initial reaction to this was to make a graph, which immediately got out of hand, but it kind of helped me understand the adjacency for the whole cube.
So can I just, okay, good. Can I just tell you a story about this? We got a lot of computer science people in the audience, and I'm old, right? But I remember when I was young, I played this game, and if you went first, you almost always won if you were a decent player. And so it was ever since this game was invented, which God knows how long it's been around, 100 years, maybe more. The question was always in the back of people's minds: if you go first, can you force a win? And that shouldn't surprise people, because in chess, I think if you move first, you have an advantage. It's hard to prove, but it seems like it's true. And that you could force a win in this game. The game is tic-tac-toe. People alternate choosing cells, and when you get the first guy to get 4 in a row wins. I think it's obvious. If somebody doesn't know tic-tac-toe, I'll be surprised. So anyhow, somebody, a computer programmer, a very bright guy, decided to look at the entire tree of possibilities for this game, and he concluded that if you go first, you can win. But it was a major advance in what computers could do. It occurred in the 70s. I think it was 76, and he spent a lot of computer hours. Back then, computer hours were expensive, computer time, and he used a mainframe on weekends. But it took months to go through the whole tree with those computers. But this was if you're a CS major, this is a classic example of something that the only way to solve it appears to be by exhaustion, and that's where computers are essential for that task. Okay, so
what game was it?
Cubic. So they spell it weird. cubic.
It sounds cool. Is it like a 3-dimensional
Yeah,
board game or something?
right. You want to you alternate taking turns, and the first guy to get 4 in a row wins. But it's such a I don't know. It's just like, I don't know, a milestone in computer application to mathematical games that everybody that generally people, all programmers know about this. They know. It's kind of nowadays. I'm sure it wouldn't take a month of computer time to do it. It would be a lot quicker, maybe a couple hours. But it's a real programming challenge to look, go through the whole tree. Okay, guys, I'm having too much fun. What am I supposed to do? I'm supposed to talk about the birthday paradox. Okay. Any more questions on the test? You guys, I'm glad you've been looking through it. I just these problems are original. Sometimes I make a mistake in how hard it is. Maybe it's too hard or too easy. It's hard to get the exact, but I'm doing my best. That's why I have 2 extra credit problems in there in case one of the other regular problems is too hard. So I'm trying to. Actually, I'm not trying. I mean, I like to be creative. I mean, that's what makes the job fun. I was telling the previous hour that somebody asked me, "What book do you use to do this problem?" And I said, "I'm sorry, it's not in books yet, and I know it's not in a paper either." It's that's in general, in every field, what's rewarded the most is creativity, and I don't mean like brainy creativity, but just new ideas that nobody else thought of that are useful, not off the wall stuff. And so I try to, in my tests, I try to bring that out of my students, who bring that sometimes it's a latent capacity for creative thought, because they're thinking, well, math, they give us a formula, and you just do the formula, and you just have to fit it into the formula. Well, let me tell you something. If I've done some math research myself, whatever you're looking for, if you're trying to do a good problem, you're not going to find it in the web. You're just not going to find it. Just like an axiom. Okay, are we ready for the next? No more questions on the test for now. You're welcome to come to my office hours at 6:30 if you want to talk about the test. If you need help understanding the problems. Alrighty, so what the heck? What is the problem we got here? This is a little bit of a hard thing. What is this birthday paradox? And where is it in the book? It's example 5 on. And this is chapter 2. And what does the I stand for? Yeah, intense, right? Because this is kind of a hard thing. It's a paradox. Paradoxical. Okay, so what is the thing? You're asking, how many people do you need to have in a room? Let's just draw a picture first so you can understand the situation. How many people do you need in that room? These people are, they're unrelated, okay? Before, the probability is what? The probability is of what? You want the probability to be greater than 50% that you have a collision. And what do we mean by collision in computer science? What does that word mean? That means that at least two people have the same birthday. And we talked about this. We were guessing and stuff like that. And somebody remembered this from a previous course. And what did they say? Do you guys remember what that person remembered? What was the answer? What do you mean? You have to have at least what? What was that strange answer? Strange because it was what? Well, then
Because it was rather small.
It was rather small. In fact, it was what?
It was only like 23, right?
Exactly. Very good memory, better than mine. So it's just 23. You say, God, how many birthdays are possible? assuming February, what is it, 29th, this off the board, there's 365 possibilities. So you would think that with 365 birthdays, you got at least 80 people before you would get a collision, right? It's not the way it works. Let me tell you what it's related to, okay, really quick, just to try to, get you thinking a little bit. Always in the news, I was watching TV, which I do to relax, that I didn't get to this little story, but somebody had won the lottery twice in a week somewhere. And, it just say it's impossible. They were cheating, that's the first thing you think is people are cheating. But if you put on your math hat or your computer science hat, you could say, there's a lot of people playing the lottery, lotteries in their states. And, maybe there's billions of people. And isn't it possible that amongst those, they hit 2 in a row? I mean, there's a lot of ways that 2 out of like 5 billion people, could hit the same, could hit the winner, in a week twice. I mean, you got to think about that, not just the fact. It's not like, what's the problem that one person hit it twice? It's like, well, what's the possibility that there was one person somewhere, of all the players who hit twice, in a week? That's sort of where this is going. So how do we set this up? So how can we do this? So we want the probability of what? So let's look at the probability of no collision with n people. So you've got n people, and of course we assume that n is less than 365. If n is equal to 365, then you're going to get a collision because it's by the pigeonhole principle. So no collision with n. So how many ways? First of all, let's have a way of encoding what we've got here. So I would let's take vectors. And this is the first person, second person, third person, and this here is the nth person. If you've got n people, how many different ways could we assign, how many ways could they have birthdays such that none of them have the same one? So you're dealing with n people, so how many ways could this happen? So let's put in some birthdays they might have. This person has 12, this has 360, 1, and 14, something like this. So how many ways can this be done such you don't get any collisions?
That would be permutations of n, I think.
Yes, but it's a little bit complicated. It's actually National Public Radio, NPR, on the calculator, because the birthdays you're drawing from, you're taking n birthdays, right, from 365. So so it's really the permutations of n things possible from 300. So you have n things of 365. Then how many permutations of that? So there's a word for that. So it's NPR 365, or is it n? Oh gosh.
Yeah, which one's n, which one's r?
Oh my gosh, how can I not know that? How can I forget it? 365 comma n. So there's 365 possibilities. We're going to choose n, and we're going to count all the permutations. That will cover all the red, guys, all the red situations. These are permutations, so you're not going to get a repeat of, when you have a permutation of distinct things, matter is neither created or destroyed. You don't suddenly get 2 of the same, numbers popping up, because it's a permutation of a subset of a set where all the numbers are distinct. Everybody's good with that, right? That's in the numerator. But in the bottom, how many ways could these n people have? In general, how many ways could n people? How many birthdays? Possibilities are possible, because the first guy could have how many different birthdays? Person one could have how many? How many? What are his choices? That's not his choice, but how many possibilities? Person one, 365. What about person two? If there's no constraint on this, we don't care about collision. Person two, he's a different person, right? Or she. And she could have been born on 365 days too. So what do I have to put in the denominator? Where do I have to put it? Well, there's 365 choices for this, 365 for this. Did you get me? 365 for the next. How many is that?
Wait, I forgot what this fraction is representing. So
This vector is representing the first.
what the fraction is going to be.
The probability of no collision.
So the numerator would be
Yes.
arrangements of the no collisions, and then
Yes,
the
right.
denominator
The
would
bottom
be
is just all possible
all positive.
ways you can have birthdays. So each person can have 365 choices, right? So I've got n of these people. So how many is that?
365 to the n.
Very good. Gosh, it's awfully quiet. I mean, I worry a little bit. I said this is a little of an intense kind of problem, right? But if you break it down with smaller numbers, I think it'd be easier. But it won't be real. But it'll be easier. Let's go over this again. For n people, this is n people, and their birthdays come from 365. And this is all the permutations possible. Permutations of n that are drawn from the 365. They're all different, right? So these are the number of ways that you could get the n people without collision. It's a lot, but it's not as big as this. So the question, how did they get to 23 here? Well, what's the story? You want to know the probability of no collision. You want that to be what? Less than 50%, because now the probability of getting a collision is going to be bigger than 50%. It's going to be, in the lingo of probability, be likely. If it's over 50%, it's likely. Sorry, this marker is going dry on me. Okay, so now comes a serious problem here, and that is, how do we evaluate this with, even if you have a graphing calculator? Because what you want to do, now that you have an inkling of what the answer is, you got to put a 23 in there. You got to put a 23, and you'll realize that probably no collision at 23 is less than 50%. And let me just tell you from the book. I hate to copy out of the book, but what the answer the book has for this. Well, somebody said 364. No, aren't there 365 days in a year? 366 with the extra day, the leap year. Right?
Well, my question was, as I thought it was 365 factorial.
No, these are just all possible. Okay, so you've got n people, right? You don't know nothing about them. So each guy could be birth, day 1 or day 365, all those possibilities. So if you're doing this in this vector style, then it's 365 choices for each of these. So that's why it's this. That's the sample space.
But then couldn't two people have the same birthday?
Right, but I'm counting here the probability of no collision with n people.
Oh, okay.
So these guys, there's no collision. This is you can have tons of collisions here. So this is my sample space, 365 to the n. Basically, those are the outcomes. But I got to look at which of those outcomes have no collision. And that's where the NPR comes in.
And what does the W and N stand for?
Oh, width. I'm sorry. I took limited space. So I tend to do W/ for width.
Oh.
With n people. Okay, so we've got a formula for it. You would get credit for doing, partial credit for this, but it happens that in our textbook, Ross will lay down a formula but not tell you how to evaluate it. So what's the first step that we should, if we're trying to evaluate this expression for n equals 23, the first step I have to understand is, what is NPR, the number of permutations? What is that? What's the formula for that? Because it's in a calculator. We know what NCR is, right? Number of combos. But what about NPR? What the heck is? What?
I think. Well, I heard last time a way to say it is NPICR. So like it's kind of like choosing individual permutations rather than just combinations.
Well, okay. So this is a number of permutations of things of n things drawn from 365. So how many ways could I draw n things from 365?
Factorial over n minus r factorial.
I could draw, and then I have to multiply by what? All the permutations. So yeah, you've got the answer already. That's good. You got the answer, but I'm just trying to so 365 factorial over what? 365 minus n factorial times n factorial, but I'm multiplying by n factorial. So these go out. So all you have to do is calculate this. And that's what you said, right? I mean,
Yeah.
Very good, very good.
I thought you were asking about just a general formula for NPR.
Yeah, I forget formulas. So I have, but that, yes, I was. So that's really good. You have that. If you have the graphing calculator, you can just pop it in. Good, thank you. See, no, that was good. So then again, so then what do we? So what is it that we have to calculate? So we have 365. Oops. 365 factorial over 365 minus 23 factorial. And all of this is over what? 365 to the 23. Okay, so we have a problem here. This is a problem. This is a lot of time, mucking around with the calculator. But I tell you this much: on my old ancient, as old as I am, this TI-89, I can actually put this in a 23 and a 23 here, and it will actually calculate this. Even though it's like infinity over infinity, it knows how to do it. 0.4927. So the answer is 0.4927 if you calculate that on your calculator. You don't have to break it down and multiply. Just put it in if you have a grapher. It knows how to do this. It knows you're taking my class and you have to do this. They put the special software in to do it. But can we just double check this here? So what exactly are we calculating? 365. I know this is not a class in numerical analysis, but could you tell me what's going on here? So it's 365 to what? 365, 364, and it goes down to what? Well, once you get to what is 365 minus 23? We get down to 342. So if I did it right, when you get down to 342, you're canceling off for this. So that means that you don't get down that far. You go to 343. So this expression, even though it's ungodly large, this is what you're dealing with. These are the numbers, and that is 0.4927. So the probability of no collision is less than 50%. Therefore, the way it goes, is the probability of at least two people with the same birthday is what? What's the lingo? I got to teach you the speech patterns of probability from Ross's book.
For this case, where it's 0.49?
Yes.
Unlikely?
Well, no.
I don't know. It's still likely, I would say. But
okay, careful. We got to be really careful because these are like reserved words in probability. When you say unlikely, it means it ain't going to happen in probability and statistics. I mean, I'm just telling you, this is the way they say it. If they say it's likely to happen, that just means that the probability of it happening is over 50%. I know that doesn't make sense to you, but this is the lingo that they use in statistics. So if you know that the probability of no collision is 49%, that's equivalent to saying the probability of a collision is
I didn't know.
likely.
Okay. I lost track of what you were asking.
Sorry, it's okay. I lost track too. So. But I'm still, as a mathematician, I hate this because I hate this because I don't know how to calculate this on my I'd like to use some mathematics to do it, and you guys should be aware. So if you read, if you're a CS major and you're going to take 482, the algorithm class, and the standard book is called CLRS, Clears. They find a way to calculate this, get an approximation. It's very good. They don't have to do this. They don't have to depend on the fact that the calculator knows how to do infinity over infinity. Math 42. That's CS 482, right? That's introduction to algorithms. It's in the textbook.
Do they also figure that out in the math version of that? I think it's 481A.
Nope. Sorry. I make enemies about this, but I feel there's not enough. A lot of mathematicians, they don't want to get dirty, their hands dirty, right, with numbers and stuff. But when I calculate something, I want to get the answer. I don't want to depend on the fact that the calculator knows this is coming.
Yeah, I'm really fascinated by algorithms, and because I'm a computer science person. But I'm questioning my decisions because I'm going for a math minor.
Yes.
And I have to take the 481 class to get the math minor. And I'm like, I don't know.
Well, the old story, again, I'll probably get fired for saying it, or, what is it? Expunged or something. I don't know. The old story about 481 numerical analysis, it moves at a glacial pace. Now, I know that it's been speeding up because of global warming, but it still moves glaciers, they move, but you can't see them moving. Sorry, I didn't make that up. I was told that it moves at a glacial pace. That was,
Don't worry, I won't blame you for that.
Thank you. I'd rather not get fired. My son he's not working. He's 18, but he doesn't do any work. He just plays game all day long. All day long,
Well, that's important.
And I said, why are you wasting all your time, Nick? He said, well, school hasn't started yet. He's in SMC. It only didn't start because he was too late to enroll in the winter semester. When you guys have kids of your own, make sure that you watch what they're doing. Otherwise, they'll find out that they missed the enrollment date. All right. Okay. Any question on this when we go on to the next topic? And look at the chat.
I have a question. I'm confused how you knew N was 23. Is it because you plugged in 0.5
That's
into the equation, or?
That's a totally legitimate question. I'm sorry. I didn't know it was 23. I just knew it because I looked it up in the book. All I'm doing is verifying that, yes, 23 is the magic number.
But could you work backwards, I'm saying? Because you know that in order for it to have a probability of, in order for it to be significant, it has to be over 50% or below 50% or something.
Okay, let me.
So can you plug it into the equation and solve for N? Is that a possibility or no? It's because you're playing with factorials here. So
help me out here. Are you a math major or CS?
I'm a math major.
Okay. Then I can answer you. An intellectually honest answer is the way that CLRS are engineers, right? So they want the answer, and what they're going to do instead of probability, they're going to calculate expectation, the expected number of collisions. And there's a beautiful way to do that. I wish I had time to show you, but everything can be done by hand except for take E to something. So you have to take some button pushing, but it's really, really slick. It's real slick, and they can get very close to the right answer. I think they get either 24 or 25, but they're real close. 20. I think they get 24. I think. I can
look up. A binomial, or what are you talking about?
They calculate an expectation. Expectation. There's two things in
you have like a true or false. You have like a 50-50 chance. It's either not or it is, and you create a distribution. Is that what you're talking about?
Because what they're going to do is calculate the expected number of collisions if you have n people. So that's a slightly different question than probability is hard to calculate. It's hard to do. Expectation is much easier to compute.
So they solve it backwards, kind of.
They do, but they're looking for something a little bit different, but it gives you a real close answer. Maybe very, very close.
So they
to
keep
20.
on making like approximations of
No. It's a
expected
simple thing.
amount.
They can do it. They solve a quadratic equation. It's like, but they're not calculating this probability. They're computing an expectation. We'll get into it later in the class, okay?
Oh,
But you'll find out that probability kind of computing probabilities is ugly work sometimes. But there's ways to get the expectation that are quick and make sense, and math majors will just love it when you see it. You say, that's beautiful, just beautiful math. Okay, what's my next stop? Let me, I'm supposed to do a problem, but I think it's too much at the moment. Okay, so let me try to help ourselves by pointing out to you a problem in the book. I'm not sure I'm going to do it completely, but just to give you a hint, it might be useful on something you're working on now. It's a hard time finding it. Sorry about the delay. Just a second. 18 on page 53. So page 53, number 18. I'm counting on you guys to have read the problems on the test. So otherwise this won't make much sense. Page 53, number 18. Now, if you're a math major, there are certain sequences of numbers that keep coming up. And if you're an engineer, like a computer engineer, you'd be surprised that some of these sequences that seem to be their natural habitat is pure mathematics, but they're actually useful in real life. I don't know, let me test your guys' knowledge of biology or science. You understand bees and drones and stuff, and worker bees and stuff like that? Do you know the ancestry? It follows what? It's the ancestry of bees, of drones, is what mathematical sequence is involved there? If you look at drawing out the ancestral tree. Does anybody know?
well, is it exponential?
Okay. This is an interesting thing, okay? F stands for what? Usually it's a capital. But
Function?
Fibonacci nth number.
Oh,
For Fibonacci, so Fibonacci type sequence. So if we look at this problem, well, I'm not even going to tell you at this moment but every sequence, if it has a generation, like the Fibonacci, it has to have a boundary, right? The Fibonacci looks back 2 and adds them. So let's just let me just put, if this was, this is not the typical way it's shown, but what do you think the next one is, if it's Fibonacci style? This is the boundary. But what do you think this next one is? How does Fibonacci work? Where you're at currently is the sum of the last 2, right? So what is it? You guys know, right? 3. What about the next one up? 5 and so forth. Okay, so this problem asks something that will be of use on the test. And it says, how how many ways could you? You're going to toss a coin n times. So toss a coin. I hope I'm not in the n times. And the question becomes, how many results where you don't have any consecutive heads? How to write that? So they say number of ways to toss. It's a number of ways to toss a coin n times without consecutive heads. Now, look, I mean, maybe that's a mouthful, right? Especially the way I wrote it. With W/O is without. I think that's universal. But what if the answer was 4? What if we're going to toss? Let's use a different color. Let's just play with this for a second. What if I'm going to toss 4 times? You toss 4 times, right? So what are the possible results of this? How many are there results? That's what? If you have 4 tosses, how many possible results in terms of sequences of heads and tails? How many you could get? How many is it? You guys know, right? How many is it? Well, it's how many? It's you got 4 tosses, right? Each one can be a heads or a tail, right? So, how many possibilities? There's 2 here, 2 here, 2 here, 2 here. We've got to count that. How many is it?
8.
Well, let's see. This is 2 possibilities. This is 2 possibilities. This is 2, and this is 2. Right? What is that? Oh, I know the problem. People are adding instead of multiplying. I kind of know this long talk after the class, the late class, or near the office hours. And I told this individual, I said, almost always you're multiplying. But think about this. There's 2 possibilities here, 2, 2, 2. They're all, in heads and tails, they're all different, right? So there's how many? 16, right? But what about this question? If you disallow consecutive heads of the 16, how many are there? If you want to be a hero, try to pop that in. Let's see if we have another hero. So how many are like put some in? You don't want to get two heads in a row. So how you could start with a head, the next one has to be a tail, and then there's 2 more. How else could I do this? I could start with a tail, and it could either go tail, tail, or you could start with a tail, and it could go heads, right? So these are the categories. So how many in each category? So how many for this? How many cases where I don't get? You guys understand the question here?
Would it be 4?
For this one?
For because the first toss would have 2 possibilities, but then the first one only has 1. Or oh no, that doesn't count. Never mind.
It's okay. It's okay. You can't put 2 heads here, right? Do you guys understand the question? Let's go back. I want to make sure everybody. This is the problem with interesting things. There's this little lag, a latency, whatever you want to call it, before you say, "Oh, now I get what they're talking about," But sometimes, if the problem is flopped down in front of you, you're like, "Oh, what?" You don't understand the question. So they're asking here in this case, if you toss the coin 4 times. How many cases do you have where you don't have adjacent heads? There's no 2 heads that are next to each other. If you want to use a fancy word to impress family and friends, you use the word successive. But then most people would say that's excessive, But you get it, right? You get it, right? So I broke it down in these cases.
That's a very high quality joke.
Well, thank you. Thank you. I hope you're serious. That would be a bigger joke if you weren't serious. And, I'm just a little paranoid now. Okay. So how many cases? So this could be anything but heads. Is that clear? So is that clear? For the next 2 guys? Because I don't want to get these adjacent heads. So how many? There's 4 possibilities. That's correct. But you can't have 2 heads. So how many is that? Do the arithmetic for me. What's the arithmetic? How many?
Well,
And-
there's 4 possible, and there's only one where they're both heads. So 3.
Good. How about this one here?
Same deal on that one, I think.
Yes, I think so too. How about this one? You know what? If you went
Different.
tail head, what does this next one have to be?
Has to be a tail.
Right. This could be a tail or a head, so there's 2. What's the total? Gosh, I'm running out of ink here. This is serious.
Oh, cool.
Oh man, I gotta ask for more reds. All right. So the answer in this case for this question, the answer is 8 if you only have 4 tosses. But what if you have n tosses? And what does it have to do with the Fibonacci numbers? Are you guys getting a feel for this now? You got to count something that's a little slippery. It's a little hard to get our hands on, okay? Like the combinatorics could get out of control unless we recognize that there's a pattern here. There's some sort of pattern. And what is that pattern? Again, why am I doing this? Not to be obscure, but hey, there's a problem on the test. I don't know if you guys have seen it, but isn't there a problem on the test that's a little bit like this? Okay, tell me if I'm dreaming or if there is a problem on the test. What problem is that on the test? Anybody seen the? Did I post up the test in your section? No,
Trying to
not a
find it.
question.
Hold on. I don't know the number off the top of my head.
Somebody said math 42. No, well, gosh, I hope I posted for you guys. Otherwise, I apologize profusely.
I'm not sure what this is like then. Actually.
Is it like the dice one? Number 5B? No.
Look at the last one. Look at the last problem, the extra credit.
Oh, okay.
We got good years and bad years, right? Right? So instead of tails and heads, we're going to have good years and bad years. So it's really the same thing, right? It's really the same thing. Okay, so if we can answer this question, we can probably do the extra credit, the extra credit. So somebody said, how is heads, tails, and heads? Okay, check that. How is heads, tail? This one here? Okay, I'm kind of unclear on that. Okay, why is that 3? Well, what are the possible? What else could it be? Let me erase Fibonacci. So we're looking at this situation right here. Well, couldn't you have heads, tail, like tall, dead men, tail, no tails, whatever. Couldn't you have this? Isn't that 3? 3 possibilities. You're saying yes to what? The dead men, tail, no tails? Okay, I'm kidding.
I mean, I definitely see it. So I made a tree diagram just to visualize it. And yeah, I'm seeing the Fibonacci sequence show up. I'm just not sure I can explain why. Just kind well, there it is.
I had a thought. I don't know how it relates, but you know how it the Fibonacci sequence takes the last 2 things into account. I don't know why the addition has anything to do with this, but taking the last 2 things into account, that's exactly the whole idea of 2 consecutive things in a row. So for some reason, there's like a connection there.
I think you're right, but I think that.
But
I think what they're doing. Okay, so I'm not going to give this to you because it's the test problem. You know, I think it's time for me to go on to another problem. But I think that what you might be looking at is you have n heads and tails and results. So if you had started with a tail, so you have n all together, right? This is so. If you started with this, then there's no constraint on what follows it, right? So if you look at the rest of this, that would be fn minus 1 number of cases, right? Because there's no front end restriction. That make any sense?
Yeah, and H, well, there's a restriction now. It's like you have to go back. Okay, I see it.
Very good, very good. Okay, now that I did God and countries, right? Because your next guy has to be a tail, right? And then now you're in that situation, even though you have a total of n, you're in the situation of fn minus 2. And you have to check that it works for the boundary condition, you know. I mean, does it give you the right number for what we did, the 8 here when you have 4? So if you check f sub 4, if we're dealing with this Fibonacci kind of sequence, you'll see that that's equal to 8. So it seems like it's working, at least for the boundary. All right, okay. I guess that's all I'm going to say on this. I'm very, very happy that we had the time to look at it. All right. Okay, if people are confused about all this abstract stuff, we did the case of 4 tosses. Do the case of 5 tosses and break it down, you know. See what you get. You're probably going to get 13. Okay. Let me check the chat, though, just in case. And while you're at it, if you guys are interested in science, look at the ancestral trees or family trees of drones, drone bees. It's related to this. I know. Okay, so what's now? Let me check the time. Hold on. Okay, so let's try to pop out something here. So I'm doing a bunch of examples, but number 53 in the problems. And I don't know what page this is. I know it's a number close to 53. I don't know, is it 51? Page 51. Yep. Okay, so this is a classic problem here. And if you don't see how to do it with the inclusion-exclusion, it's horrendous. So let's read the problem. 4 married couples. So you have 4 married couples. Let me just make sure I got the right problem. If they're ranged on a bench, sit on a bench. Okay, the question is, how many ways can they do this? How many ways? So that no couple sits together.
These are very unhappy couples, aren't they?
Well, actually, it could, alcohol flows and gets drunk and all this stuff, and maybe it's better. Having been married a few times myself, maybe in social situations, sometimes it's a little space can avert a disaster. Anyhow, how many ways so that no couple sits together? Well, the main problem with this kind of problem is getting in the ballpark, right? So I like to draw some kind of picture. Let's draw a picture here. So 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So these are the seats, okay? And just to make sure, if you say that wife 1 sits somewhere, then husband 1 has to sit somewhere besides the two seats that are adjacent to his wife. And the thing is, this gets complicated. Why is it complicated? Why does this get complicated? What's the reason? Why does this? There's something about this that looks weird, right?
It's the whole thing again.
The whole what?
Because we're kind of computing that whole two things in a row again, aren't we? Or
It's there's something. Okay, if we just look at this problem, there's something weird that can happen. In this case, wife one, there's two no-go places for husband one, right? But there's a problem. This happens a lot in mathematics with the so-called boundary condition. Where could wife one be where there's a different story, you know? 1, 2, 3, 4, 5, 6, 7, 8. What if wife one was here? Then how many excluded spots are there? So it seems like it's spatially dependent on, this problem has a lot to do with the ends of the table. And this, if you're a computer science person, which most people are, and you try to use recurrences to do this, you will find that it does not end well. You know, you get all, you can solve the problem up for 3 married couples, you know, and then try to go from 3 to 4, 4 to 5, 5 to 6, and so forth. This is a problem. It's a problem. So this is it's a classic problem that's approachable by the inclusion-exclusion formula. And I be honest with you, I'm not, you might say, why are we doing such hard problems? Well, I don't know about you guys, but I have a mental inertia, and I won't learn something unless I have to do it. In other words, there's no other way to do it. So, of course, when I first encountered this problem, I said, I'm going to use recurrences because that's what I teach in Math 42. But I would not have learned the inclusion-exclusion formula unless I had been forced to do it by this problem. I don't know of another way to do this. So let's see. What do we want to calculate? They really want the probability. I really want the probability here. Want the probability of no collision. What constitutes a collision? Some husband is sitting next to his wife, or the other way around. I don't want to sound biased here. So that's so really, this number we calculate, we'll need that to determine this probability. Okay, this is what I really want. Okay, so what's the technique? What's the technique? We want to define some events. So what should event E1 be? It should be in a place where it's not going to get cut off by the glare. So E1 will be what? Husband, couple one sits together. That doesn't, I don't know how to handle this. This is the problem. I think you understand this 4 married couple. How many people is that altogether? That's 8. So I need to get a little space. So E1 will be what? Is couple one together. And hopefully that fit in there. It didn't really, but this is couple 2. E3. Couple 3 together, and 4. Couple 4 together. Okay. We got some events. Now comes the first crux. We're looking for what? We're looking for the probability that no couple sits together. What would be the complement of that event? Okay, the event is the problem.
Which event?
Okay,
sorry.
The no couple sits together. What's the complement of that?
All couples sit together. Or no, some couples sit together.
At least one.
Yeah.
You got to use that term. You know, somebody should have some fun. Take the entire book and figure out how many times the phrase "at least" shows up. It's got to be at least 1,000 times he says that.
I think I like the word some. Like when that's interesting. Yeah.
It's like a logic thing. The opposite of all is some.
Yeah.
Where some means at least one.
Yeah.
But yeah, I'm starting. I have no idea how to do this problem. I'm trying to figure it out myself. But I like this event thing. So we just need one of those events to happen.
Right, but it could also but also it could be that right. What if two of them? I mean, it could be right.
Yeah. So I'm
But
starting to see how inclusion exclusion plays in here.
But before you do that, this is the crux. Okay? No, you're right there. I want you to get it. I don't want to tell you how to do it. What would be the set? How would we describe the set where at least one couple is adjacent? How would we what set would that be of these events? So these are events, right?
Oh, union of all of them.
Okay, you're right, but let's hold on. Let's get everybody. That was pretty quick.
Union of arrangements where all of them, or the union of all of the I don't know. Yeah. of arrangements where one of those or more happen.
Yes, but is that? I lost the other aim. I lost her for a second. Are you good? Are you good with what he's saying?
Yeah, no, I'm good.
So what would you write then exactly in the notation?
Well, what I'm writing down on my paper is E1, Union E2, Union E3, Union E4.
Right.
Or yeah, you could do you could use that notation. That's fine too.
Now is this? Yeah, go ahead.
And then I'm writing down the inclusion exclusion definition there, which is going to be really long.
Right, but let's. I just wanted to make sure we got to be careful. Are we calculating the complement or the actual?
So, well, I mean, then in that case, it would be 1 minus the whole thing.
Probably that. Yeah, exactly. So we're going to get the thing that gets subtracted, right? That's what we're going to figure out. This is the case where there is at least one collision.
Right.
So we have to take the probability of this.
So, so E is. Well, what is E? It's each of those E's. There. Are they each a set of all the possible arrangements where that thing happens?
E1 is the event.
It is an event.
You get a random. You think they sit randomly, so it's the event that.
Okay.
It's the event that couple one is sitting together. It doesn't mean that anything about couple two could be sitting together too. But this is just couple one is together.
But since we're unioning them together, then they're actually sets, right? Sets of all the possible.
Well, this is say so. This is E1, E2. So at least I think, as Amy had said, at least one of these for this to be. If you're in here, in this set, at least this is the outcome that at least one couple is sitting next to each other.
No, I know that. I understand that conceptual part of it.
Okay.
So does that mean that it looks like we're treating all the different E's as sets. So are
there's you see this event is think of it this way. There's a sample space, right? And that's like a musical chair situation. Everybody sits wherever. In fact, how many ways could
this is the set of like E1 is the set of all arrangements where couple one is together?
Well, it's yes.
Okay.
So what is the sample space?
Now it makes sense to me.
How big is the sample space? So I mean, think about it. You've got how many people here? We got 4 couples, so this is not a Stepford wives situation. Everybody's different. All the wives are different. So you got four. That's 8 people, right? How many ways can 8 people be seated on that bench? I mean, just to check that everybody's on. How many ways could, regardless of all these extra conditions, just any seating? You got 8 people. How many ways can you sit them down on that bench?
Factorial.
Yes.
Brandon put it in chat too.
Right. Good. Yeah. So that's important that we know. But so when you think of E1, it's like which of those 8 factorial arrangements have the property that couple one is adjacent. I think you know that now. I think you're good for that. Oh my gosh, we're out of time. We, believe it or not, we're having so much time. Time flies when you're having fun. Miss Janet Jackson. Right?
We can, well, I mean, we could leave it as kind of a thought exercise, like homework, quote unquote, for next time.
It would be a pretty hard problem because you're gonna. First of all, there's only a numerical answer in the back of the book, and this is an actual question and exercise in the book, so they don't tell you how to do it. But I would tell you, just let you go. You have to use the inclusion exclusion formula.
Yeah.
And so
and that can be pretty big and nasty, especially for 4 different things. But
what's better than 10 different things?
Right. It can be done. Like I'm already kind of like doing it and like figuring out for intersection of 2, intersection of 3, and stuff like that.
Okay, just the last thing I'm going to say. What do you think the answer is?
I don't know.
No, I mean intuition. I mean a number. So you got these 4 couples. Do you think it's at all? You think it's very rare that they all would be separated from their mates?
I think it's kind of rare. I'm guessing around about the 4 factorial ish.
Just give me a number. I want a number for percentage.
I'm thinking is like 20. I don't know.
Anybody else?
Oh, sorry. I was thinking about how many.
Oh, I want a percentage. What's the chance?
Percentage
what's
of
the chance that no couple is sitting together? Doesn't that strike you as being a pretty rare thing?
Yeah, put me down as 12%.
Okay. Anybody else want to guess? Just something to make it interesting for the next time. 33%. Okay, if you say 33%, think about this. What if this is a real situation? You've got these 8 people, the 4 couples, and they just randomly sit down. Don't you think it's kind of unlikely that none of them would be sitting next to each other? This is one of those funny things in mathematics, right? It's hard for us we don't have an intuitive understanding of this because we just don't. Probability is like a weak. We don't have the intuition to handle this kind of problem. This thing in evolutionary sense has not come up enough where we can get close. So I'll leave it at that. I appreciate you guys coming, hanging in. Some people have already left, but thanks, Ed. Work out this problem and see if the answer makes any sense to you. Okay, you would think the number has got to be really low, right? I mean, there's 8 people. I mean, that's pretty well mixed up. I mean, wouldn't that be kind of unusual for them all to be separated? Just with those 8 chairs. Okay. Okay, you guys keep on working on the test. If you get stuck on the test, I'll see you tonight at 6:30 if you need a little boost or something. But I really, really appreciate your attending, and this is I really appreciate your participation. I really do. All right, you guys. Any last? I'm here for if you want to. Because I don't have anything after this, but I want to let everybody go that needs to go.
Okay. Thank you, Professor.
All right. Thanks, Alan.
Messing with this one. See you next week.
All right, yeah, but hopefully, are you in a group, Aim, for the test?
I actually haven't gotten a group yet. I don't know. I'll see if I can find people.
I'm afraid that some of the problems may be very difficult. More so than I intended.
Yeah. So I've looked it over, and a few of the problems I'm just like, what? And I will have to spend some time thinking about it. But
this is the cost of being original. Sometimes it's
right. But as a teacher, like this is kind of, I look at this and I go, this is a good take-home test. These are, with a take-home test, you want to have a week to do it and time to think about it and mull it over until you can come up with an answer. So, as opposed to like this is the only kind of test where you can ask those kinds of questions.
That's correct.
If it was an hour-long test, these would be very unfair. But it's not an hour-long test.
My colleagues are very irritated by this because they've had some of the students before in other classes. Students will ask them how to do it, and there's nothing like if a person has a balloon, blimp-sized ego. There's nothing worse than a student asks a question of a lower division class, like whatever, non-graduate class, and they can't do it. That's just.
I remember I think it was like Carl Sagan or one of these science guys who one of their favorite anecdotes was when they were in college and asking their professors, like a lower division physics class, asking their professors how to do this hard problem. And the physics professors would look at it and go, I don't know. Let me think about it for a while. So like physics problems can be hard no matter, how much experience you have. Like they can always throw something else at you. And I think there's a lot of stuff in math and probability that's the same way.
But physics is known to have that property to be
absolutely.
To be hard.
Physics is known.
It's known to be hard, really hard. And I'm not coming up with this. There was one of the world's greatest mathematicians told me this. He said that the subject is just awful in terms of conceptually, to get it.
Yes. Yeah. Physics especially has, it feels intuitive and then it's not. So that's the dangerous part about it is you think you understand it, but then you realize you don't. There's a huge thing. Like I follow a person who teaches physics. Like they make their whole thing is about making videos for teaching physics. And what he found is if you make videos that people kind of nod along with and agree, yeah, I see where you're going with that, they tend to not understand it. But if you throw in things with misconceptions,